Hello. This video lesson is going to be a discussion on the structure of group homomorphism in our subject, Foundations of Mathematics. Okay. In abstract algebra, homomorphism is a function between two groups that tells us that those two groups are similar in structure. If we look up on the internet to find information about group homomorphism, this is the first example that we come across. Let's pick this example and let's try to understand what is this all about before getting into the textbook formal definition of homomorphism. The group of integers is an infinite group, while the group of integers modulo 3 is a finite group. So it's tempting for us to think that these two groups have absolutely no similarity. Let's get a little deeper into both these groups. The group of integers modulo 3 contains three elements: 0, 1, and 2. On the other hand, the group of all integers can be expressed as a union of all the multiples of 3, 1 plus all the multiples of 3, and 2 plus all the multiples of 3. If we add any two multiples of 3, we get another multiple of 3. If we add 1 plus a multiple of 3 and 2 plus a multiple of 3, we get another multiple of 3. Similarly, if we add 2 plus a multiple of 3 and 1 plus a multiple of 3, we get another multiple of 3. Similarly, we can check that these results are in the exact same manner. If we replace all the multiples of 3 by 0, we end up getting the same numbers that the group of all integers modulo 3 contains. This similarity between these two groups is caused when we assume that all the multiples of 3 get transformed into 0. 1 added to all multiples of 3 get transformed into 1, and 2 added to all multiples of 3 get transformed into 2. Mathematically, this transformation denotes a function between these two groups. Mathematically, this transformation denotes a function between these two groups that takes values from the first group, divides these values by 3, and then gives out the remainder obtained therein, which eventually becomes members of the second group. Such a special function on a group theory is called a group homomorphism, or simply homomorphism. For a formal definition, a function f from a group A with binary operation single asterisk to a group B with binary operation double asterisk is said to be a homomorphism if, for any dual elements x and y of the first group, f of x single asterisk y is equal to f of x double asterisk f of y. In our previous example, the identity element of the group of all integers is 0, and the identity element of the group of integers modulo 3 is also 0. The given homomorphism maps the identity element of integers to identity element of integers modulo 3. This is the fundamental property of group homomorphisms. A homomorphism between two groups maps the identity element of the first group to the identity element of the second group. The connections of all these elements of the first group which gets mapped to the identity element of the second group is called the kernel of that homomorphism. Since the identity element of the first group always gets mapped to the identity element of the second group, so the kernel of a homomorphism can never be an empty set. It must always contain at least one element, which of course must be the identity element of the first group. If it can somehow find another element in the first group which also gets mapped to the identity element of the second group, then we can clearly find that this function is not a one-to-one function. A homomorphism between two groups is one-to-one if and only if the kernel of that homomorphism contains only the identity element of the first group. In other words, the identity element of the first group is the only element of the first group that gets mapped to the identity element of the second group. Okay, so let's have another example. Let's take the group of integers, which is obviously an infinite group, and a finite group containing two elements, -1 and +1. The group of all integers can be represented as a union of all the odd numbers and all the even numbers. If we replace all the odd numbers by -1 and even numbers by +1, we end up getting a group that looks quite similar to the second group. Mathematically, we take a function between these two groups that takes all the odd integers and gives out -1, and takes all the even integers and gives out +1. Such a function that makes two completely different groups looks similar to each other is called a homomorphism. The existence of such a homomorphism between these two groups guarantees that these two groups are similar, and that the group of integers is homomorphic to the group containing only -1 and +1. A homomorphism is a function between two groups which may or may not be one-to-one and onto. If it does become a one-to-one and onto, we no longer call it homomorphism. Instead, we call it isomorphism, which was assigned to another video lesson. If it can find the homomorphism between two groups, we say that those two groups are similar in structure. But if it can find isomorphism between two groups, we say that those groups are identical in structure. Okay, so thank you so much for listening, and that's all for my video lesson for this topic, the structure of group homomorphism.